Section 1G, scientific notation. So scientific notation is a way of writing numbers that allows us to express either very large numbers or very small numbers. If you remember when we were talking about decimals in large numbers, we said we could take something like 6,700,000 and rewrite that as 6.7 million. So this was a way to abbreviate large numbers. Scientific notation is the same type of thing, but instead of saying million, in scientific notation, this would be 6.7 times 10 to the 6. So what exactly does that mean? Scientific notation basically is built of a couple different pieces. The first piece is this section right here, which is a decimal number between 1 and 10. Smallest side being 1, largest side being just below 10. Meaning it can go up to 9.999999, but it can never reach 10. So basically you're going to have a single digit ones place. So we can kind of substitute that with an X here. And then we may have some decimal places involved. So that's the first part. Then we multiply that by 10 raised to some power. I'm going to use an n for that. But raised to some power. So that's basically 10 times 10 times 10 times 10, however many that power is n. So in this case, we're saying 6.7, that's a number between 1 and 10, times 10 to the 6, which is the same as saying 6.7 times 10 times 10 times 10 times 10 times 10 times 10. 1, 2, 3, 4, 5, 6 of them. When we multiply that out, we get 6,700,000. But that's basically what scientific notation is doing. It's taking a number such as this 6.7 million or 6,700,000, and it's breaking it down into these two pieces. The decimal part that is between 1 and 10, and multiplying it by 10 raised to some power. That power determines how far we're going to shift the decimal point in this. If we look at this number right here, and that's where the decimal point would be for 6,700,000, that's where the decimal point would be. If I go and I move over that decimal point to get it over here to make it 6.7, we go 1, 2, 3, 4, 5, 6. I moved it 6 places. 6.7 times 10 to the 6. Now, why do we do this? Well, same reason we say 6.7 million instead of 6,700,000. It's quicker to write, it's easier to deal with, and as numbers get larger and larger, 7.8 trillion, it's a lot easier to do that. And here we're putting it in numerical form, but we're doing the same thing. So let's look at dealing with scientific notation. Get that board somewhat clean so we can see it. Okay, so let's take a number in scientific notation and look and see what happens here. 3.62 times 10 to the 4. So this is a number in scientific notation, And we know that because this number is between 1 and 10, right? 3.62 is in between 3 and 4, so it's in between 1 and 10. And it's multiplied by 10 to some power. Now what I showed with the previous one is this power, in this case the 4, tells us how far this decimal point was moved. So 3.62 times 10 to the 4 is the same as 3, and then if I were to move this over 4, 6, 2, 0, 0. Notice that decimal point from here, 1, 2, 3, 4, puts me at my 3.62 again. So when we are dealing with large numbers, the exponent, or power of 10, n will be positive. So if we're dealing with large numbers, then the power of 10, in this case n, will be positive. And that tells us from the scientific notation that we're going to move that decimal point to the right by 4 because that's going to give us a large number, or to the right by n in the generic case because it's going to give us a large number. If we're dealing with very small numbers, so numbers between 0 and 1, then that power n is negative. So that n would be negative, which means that we would shift the other direction to make the number very small. So let's look at a few examples of these. .3 times 10 to the 6. 8.3 times 10 to the 6. This is in scientific notation. Let's put it in standard notation. Remember, standard notation is just when we put things into numbers. So 8.3 times 10 to the 6. We look at this exponent and we see that it is positive, which means we're making a large number. So this decimal point has to go to the right because that's going to make this a large number. And it goes to the right by 6. So it is equal to 8, 3, 0, 0, 0, 0, 0. And all I'm doing as I do that is I'm counting how many places. I could even take that 8.3 if it makes it easier for us and just go 1, 2, 3, 4, 5, 6. Fill in some zeros. Right, fill some zeros in there. And now we can see that we have 8300000, 8300000. So we're just moving it over that many places. So when you're first getting used to writing numbers in standard form from scientific notation, by all means, just bounce that decimal point over as necessary and fill in with zeros and then write out the final answer. As I have been dealing with scientific notation for years, I just work my way across, but feel free to take these intermediate steps. 1.74 times 10 to the 2. 1.74 times 10 to the 2. We see that this 2 is positive, so we're making a larger number. So the decimal point is going to move 2 places to the right. 1, 2 gives me 174. 9.4 times 10 to the 8. Again, positive power or exponent. 8 says I'm going to move the decimal point 8 places. Since it's making us a large number, that's going to be 8 places to the right. So I go 9, and I can say there's 1, 2, 3, 4, 5, 6, 7, 8. And then I'll just put in my commas to separate the periods. Remember the ones period, the thousands period, the millions period, to tell me that 9.4 times 10 to the 8 is 940 million. So not too bad going from scientific notation to larger numbers. Well, how does that work with smaller numbers? Remember I said that if we're representing a large number, then the power is going to be positive. If we're representing a small number, the power is going to be negative. So let's have an example of that. 5.8 times 10 to the negative 3. Well, now we have a number between 1 and 10, right? So times 10 to the negative 3. This negative sign right here, let me just point an arrow at it. That negative sign right here is telling us that we're going to be dealing with a smaller number. If we want this to be a smaller number, that decimal point is going to move to the left. And it's going to follow the same thing of it moves to the left by 3 places. So it would go 1, 2, 3. So we have 0 point, right? The decimal point's there. 0, 0, 5, 8. 0, 0, 5, 8. See what I did? I moved the decimal point 3 places to the left. 1, 2, 3. And then I filled in 0, 0, 5, 8. 0, 0, 5, 8. So I'm able to go to a small number from this number in scientific notation. So why do we do this? Well, for the same reason that we did the abbreviated with decimals for large values, 8.7 million, we do it because you get numbers that are so hard to represent otherwise, or you have to write a whole bunch of zeros. If I have 1.4 times 10 to the negative 12, well, what is this telling me to do? It's telling me I'm going to move this decimal point 12 places to the right. So if I write that in standard form, this is going 12 places to the right. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's a lot of places. So then I've got 0 point, and I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 zeros, followed by this 1, 4. Wow, that's a pretty ugly looking number. So using scientific notation definitely makes it nicer for us. Now, a little trick that you may get used to is when you're dealing with numbers that are small, that have that negative exponent when they're in scientific notation, you can actually count your way out to the first number. Notice with this being 12, that when I move this over 12, one of those places was the ones place. And then the other 11 of them got filled in with zeros. So using that thought process, we can say, oh, if I want to write this out without having to do all this stuff here, then I can just put one less zero in front of it after the decimal point than whatever this number is. So this is 12. I say, okay, so that's 0 point And then I do 11 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 zeros, and then my numbers that are there. Such as 7.3 times 10 to the negative 9, I say, well, the negative tells me I'm going to a small number, so I'm going to be moving the decimal point to the left. 9 tells me that I'm going to have 8, 9 minus 1, 8 zeros in front of it. So I have 0 0.1, 2, 3, 4, 5, 6, 7, 8. Oh, sorry, 8, 7, 3. So 0.0000000073. So that's a way that I can go from scientific notation to standard notation. If we're dealing with whole numbers and dealing with really large numbers, if we just have a whole number here instead of 1.74, if we just had 6 times 10 to the 7, then the same thing could work, but we look at it as, whatever this exponent is, we're going to add that many zeros after it. But that method only works if you're dealing with a whole number. So with 6 times 10 to the 7, I can just say that's 6, and then 7 zeros. 1, 2, 3, 4, 5, 6, 7, and I can put my commas in place, and this represents 60 million. So that's going from scientific notation to numbers in standard form. Let's go the opposite direction, numbers in standard form into scientific notation. Now, with understanding what we did thus far with scientific notation, then taking numbers in standard form and turning them into scientific notation should actually be pretty straightforward. So if I have 1746000, and I want to put that in scientific notation. Remember, scientific notation is created by two parts. A decimal number between 1 and 10, and that multiplier, 10 to the something. So we're dealing with a large number. I want to turn it into a decimal number between 1 and 10, which just means I'm going to put a decimal point in between the first two digits. So 1.746. I'm going to multiply that by 10 to the something. Since this is a large number, we are going to make that exponent positive, and it's just how many places did I need to move that decimal point to get there? So that's 1, 2, 3, 4, 5, 6. We had to move it 6 places. So 1.746 times 10 to the 6. So we just break it into two pieces. Take this number and turn it into a decimal with a number in the ones place, so make it a decimal number between 1 and 10, and then count how many decimal places we need to move the decimal point, or how many places we need to move the decimal point, and that becomes our exponent. If we're dealing with a large number, the exponent will be positive. If we're dealing with a very small number, the exponent will be negative. 8400, so 8,400, represented as a number in scientific notation. We want to turn it into a number between 1 and 10, so 8.4 times 10 to the, we move it 1, 2, 3 places, 10 to the 3. What if we have a really small number, 0.00000042? Again, turn it into a number between 1 and 10, so this 42 over here becomes 4.2 times 10 to the, now we're dealing with a very small number, so we have a negative in that exponent or that power. And how many places did we move that decimal point? 1, 2, 3, 4, 5, 6. 4.2 times 10 to the negative 6. What if we have 0.000000 0.975. Turn it into a number between 1 and 10, 9.75 times 10 to the, we're dealing with a very small number, negative. And then how many places do we have to move that decimal point? 1, 2, 3, 4. 9.75 times 10 to the negative 4. Let's determine if a number is written in scientific notation. 6.71 times 10 to the negative 3. Is that written in scientific notation or not? Scientific notation is broken up into two pieces. A number between 1 and 10, 6.71, that part's good, multiplied by 10 to some power, and we have this multiplied by 10 to the negative 3. So yes, that is a number in scientific notation. 18.3 times 10 to the 6. Is that a number in scientific notation? Scientific notation is broken up into two parts. A number between 1 and 10. No, not between 1 and 10. It is multiplied by 10 to some power, but this number is not between 1 and 10, therefore it is not. So I'm going to say, yup, that's scientific notation. No, that is not. 0.59 times 10 to the negative 4. Is that in scientific notation? 0.59, we're looking for a number between 1 and 10. 0.59 is less than 1, so no, that is not in scientific notation. 3.6152 times 10 to the 7. Looking for a number between 1 and 10, yes. Multiplied by 10 to some power, yes. That is in scientific notation. What about 8.41 times 10 to the 0? Looking for a number between 1 and 10. 8.41 is between 1 and 10, that's good. Times 10 to some power. That is a number in scientific notation. That is 10 to some power. The power happens to be 0. So yes, in scientific notation. Let's take a look at this and see what that tells us though. 8.41 times 10 to the 0. If we want to put that into standard form, well, what do? That says we're going to, there's no negative sign, so we're going for a larger number, right? There's no negative sign, so we're going to move the decimal point to the right by however many this number is. That's a 0. So in standard form, what is that? Well, if we move this decimal point 0 places, we end up with 8.41. 8.41 times 10 to the 0 is the same as 8.41. But it was in scientific notation, so life is good. Let's talk a little bit about calculators in scientific notation. Because this is good when we're writing it out. It's pretty straightforward that we may have numbers in a certain way. So if I say 5.62 times 10 to the 12, that's pretty easy to follow because that's the way we see it. Calculators don't always display things the same way as we see them in real life. So let's just look at an example of using a calculator and what it may do. In fact, calculators may put things into scientific notation if the number gets to be too big or too small for it to display on its screen. So you may do calculations and not be dealing with numbers in scientific notation, and then all of a sudden, boom, your calculator gives you a number in scientific notation. So let's try this example. What if I have 1, 2, 3, 4, 5, 6, 7, so 1,234,567 times 3, 4, 5, 6. 789. So multiplied by 3,456,789. So if I have that number and I plug it into a calculator. So first thing, if I plug that into a TI 30X2S, that's a calculator that I actually recommended to you, right? TI 30X2S, what will that show me? Well, that's going to show me the following. 4.26763 7625, and then it's going to show a little times 10 and have a 12 up there. So that's not too bad. It follows pretty closely to how we would write that ourselves. We would probably round it a little earlier, maybe to 4.27 times 10 to the 12. But it does this small times 10 and then puts the 12 up there. Relatively easy for us to recognize as scientific notation as long as we're familiar with scientific notation. So that's the Texas Instruments calculator. What if I go to Google? So if I go onto Google and I type in 1,234,567 times 3,456,789, it pops up a little calculator screen and shows me 4.2676376, and then it shows a lowercase e plus 12. They're using this lowercase e as the same thing as this times 10. So that lowercase e is meaning times 10 to the, and then the plus 12 is that positive 12. So these are the same thing. You can see that they rounded this a couple decimal places earlier. This number is rounded too, but on the TI 30X2S, it gives you that many decimal places, and then it's able to do this. On Google, they rounded it a couple decimal places sooner, and then they use a lowercase e plus 12. Well, what if I go to a graphing calculator? You know, one of those big fancy calculators that has the big screen and can do all sorts of graphs and everything else. Well, if I plug it into a graphing calculator, then I get 4.267637625, just cheating and looking, 36. And then I get a capital E, 12. So that graphing calculator actually took me out a couple more decimal places than the Texas Instruments calculator did. And then it used an E again. Look, see, it used it, but it used a capital E. And then the 12, telling me the exponent is 12. So different calculators may display it in different ways. So you want to become familiar with your calculator. A good practice thing is try this. Type a number like this into your calculator and see what the result is. It should represent something like this, but the question is, will it use a lowercase e? Will it use a capital E? Will it give you the times 10 written out? It's always good to become familiar with this because you never know when you're going to do a calculation and all of a sudden it's going to give you something in scientific notation. And I see it happen many times where students will do some calculation in things like statistics or otherwise where they have to use things like factorials, where you're multiplying a whole bunch of numbers together, and all of a sudden they get a result, 3.5 times 10 to the 8, and they don't know what that means, and so they put the answer down as 3.5 instead of putting that whole thing, which means they gave a number that was off by 100 million. So be familiar with scientific notation and recognize how your calculator will represent that. So that's topic 1G, scientific notation.